The following program is brought to you by Caltech.
Well, thank you, Michelle. I'm going to be introducing Dr. Golombek. So first, good afternoon, everyone. Thank you for coming. Today it is my pleasure, as I said, to introduce Dr. Matt Golombek. Dr. Golombek is a senior research scientist from Jet Propulsion Laboratory who has had an outstanding career exploring the geography and geophysics of Mars. And he has held several key leadership roles on various NASA rover projects. As part of NASA's Mars exploration program, Dr. Golombek is the landing site scientist and the project scientist for the Mars exploration rovers. He was also the project scientist of the Mars Pathfinder, which was the first rover to ever rove on another planet. He has received numerous awards for his many accomplishments, including the NASA Exceptional Scientist Achievement Medal, election to Fellow of the Geological Society of America, and even has an asteroid named Golombek after him. The city of Hackensack, New Jersey, even proclaimed a Dr. Matt Golombek Day in his honor. Today, Dr. Golombek will be speaking about how to select a landing site on Mars based on remote sensing of physical properties of surface materials on Mars. Please join me in welcoming our speaker, Dr. Matt Golombek.
Well, good afternoon, everyone, and thank you for coming. I have a confession. I consider myself a Martian. Martian is someone who lives here on Earth but works totally on Mars. And I would say I'm the longest-standing Martian that is here on Earth. So for the last 20 years, I've done nothing but work on Mars. And if you think about it, this is the first time in human history when there's been enough work, okay? Enough work to support someone to do nothing on Mars. And of that 20 years, I spent about half of it on Mars. That is, as a science team member of various rovers that are actually exploring the surface and making decisions on almost a daily basis about what to do next. So there you are, I'm a Martian. So when we select landing sites on a planet, basically what we're trying to do is infer the surface characteristics using remote sensing data. I'll go through a variety of examples. Basically, in the last 20 years, I've worked on all of the site selection efforts in detail that have occurred, from Pathfinder to the Mars exploration rovers to Phoenix to MSL. And I'll go through each one of those in sort of a snippet to give you an idea of what went on during those, and then get into the meat, which should be what this is most about, which is how you estimate the important properties of the surface, important to landing and roving, using the remote sensing data and the relationships to those signatures to the landing sites. Talk a little bit about the MSL selection, and then the one that we're in right now is for the InSight lander. So why would you select a landing site? Well, it's better than random, right? If you don't know where you're going, you could cause problems. The mission will fail if you don't land safely. So you must include safety as your #1 priority when you select a landing site. Why? Because the mission costs a lot. These missions cost from anywhere from several $100 million to more than $3 billion. So there's a lot of money that's going into them and a lot of time and energy. You have to do it during project development. You may think you understand what a spacecraft can handle, but until it actually gets built and tested, there could be differences in what you think it is versus what it turns out to be. So you have to do it while the project is developing so you can react to that. And the capabilities of that spacecraft will change. How do you do it? Well, you're looking to map the engineering constraints, which is how this spacecraft comes to rest on the ground into things on Mars that you can measure or estimate or infer. And you must define those sites. You must gather information to certify that those sites meet the requirements as best you can. What is a safe landing site? It's a smooth, flat, in quotes, boring, rock-free plain that is safe for landing and roving. Now, scientists want more exciting things, but the engineers require this for safe landing. And if you don't land safely, of course, you get no science. So that's it. You must also address the science objectives of the mission, and you must comply with planetary protection. There have been 5 site selection efforts in the modern era, and Pathfinder was about 20 years after the Viking Landers, which was our first foray. It was really basically an educated guess at what the surface would be like. The highest resolution images could identify a football stadium and nothing smaller. And what the engineers wanted to know was how many rocks were bigger than a half-meter high. So how do you go from 40 meters per pixel down to a half-meter high rock? We were able to target images using the Mach camera, about 3 meters per pixel, and that gave us a much more informed idea about what we were going to find. Phoenix was an example of what you can't see can hurt you, and I'll go through that example of all of a sudden going from 3 meters per pixel images to 25 centimeters per pixel image. It might as well have been a different planet. And finally, with MSL, there really were no surprises. Everything we found when we land there, in terms of the surface characteristics, were exactly what we had predicted from beforehand. So why is it important? Well, ground truth to remote sensing data. The better you can go back and forth between these, the better you can understand where you can land and where it's going to be safe. And it's obviously critical for any Mars exploration program. Here are our 7 successful landing sites on Mars. And you can see right off, they mostly are in low elevations. Okay? So Mars has a thin atmosphere. It's thick enough that you have to use it to land. You can't ignore it. It's thick enough that you can't just use retro rockets. You have to use a parachute. You have to use an aeroshell. But then it's not quite enough to slow you down completely on the parachute that you don't need anything else. So it requires a very complex suite. And the lower in elevation you are, the more atmosphere you have, the more you can slow yourself down, and the more you can get to a correct terminal velocity. So all of the landing sites are at low elevation, and elevation is the #1 most important engineering constraint on selecting a landing site. The second is that half of them are solar powered. 1, 2, 3, 4, except for that one. They're all near the equator. You want as much power as you can possibly get, and you want to be at the subsolar latitude for the life of the mission. So you tend to be clustered around the equator. And even that's true for VL1 and 2. These are RTG powered, but you still had thermal management issues. The temperature on Mars day-night cycle was 100 degrees Fahrenheit. You're using the energy from your RTGs to put energy into the battery to keep yourself warm at night. That's what the job on the surface is. Keep yourself warm at night. And Mars, unfortunately, never got the memo about wanting low places at the equator. What it has is low places in little itsy-bitsy spots near the equator, but most of the low spaces are in the northern hemisphere. And most of the southern hemisphere is 6 kilometers higher and much, much rougher. And that creates a very interesting dynamic that you'll see. So here's the Mars Pathfinder landing location. The ellipse, this is a 2 sigma ellipse, is 200 kilometers by 100 kilometers. And you can see it's located at the mouth of a giant catastrophic outflow channel called Aras Vallis. Aras Vallis, water about equivalent to that within the Erie and Ontario Great Lakes combined, rushed out of the ground and carved this channel in about a 2-week period. And judging by its location near the mouth of this channel, we expected that this site would be a depositional plain of materials carried from the ancient highlands that we could look at with our rover. Our rover could only go 100 meters or so, and we wanted as many rocks as we could get within our spot. That's the spot we selected. Here's the higher resolution image of the ellipse. You can see these streamlined islands, which were caused by erosion by those catastrophic floods. And the highest resolution images are shown here, about 40 meters per pixel. And that's what we had to select the site. But we had to select a site. That was a lander. And we made a variety of predictions based on the data that we did have that said it's going to be a rocky place. We know that. It's going to be a little less dusty than the Viking sites, and it should be composed of a depositional plain that was deposited by these floods. And here's one of our first images, and we have streamlined islands in the background eroded by those catastrophic floods. We have imbricated rocks, which are stacked by the high velocity fluid flow, and basically everything we saw here seemed consistent with that. So when you're the landing site scientist, you only get to choose the next one if your last one was successful. Okay? You're only as good as your last landing site selection. So this gave me the rights to select the next one, which were the MER, the Mars Exploration Rovers. They used a similar method, again, an a parachute, solid rockets to fire just before letting go of an airbag enclosed lander. Here's the landing sequence. Basically, as the radar altimeter measures the closing velocity, you inflate the airbags, you drop it down on a tether. At the right elevation, you break the tether, the airbags bounce 60 to 100 times. You roll to a stop, you open it up, and out comes your rover. And the engineering constraints were not that different from Pathfinder. These are the preliminary ones. Elevation had to be low. Latitude had to be between 15 north and 15 south. Low altitude winds became important. Surface slopes became important because of spin up during bouncing. And rocks are always an issue. Rocks are always an issue. Anything higher than a half a meter could exceed the depth of bend of the airbags and impact the lander. Here is 15 north to 15 south. The minus 1.4 kilometer elevation is right in this green, and we selected Meridiani and Gusev. And the reasons we selected Meridiani and Gusev are shown here. So here's 15 north to 15 south. Anything in gray is too high. Here's the areas we had to choose. Here are the size of the ellipses that we placed down on the ground. Went through a big selection effort that included the science goals of the mission, which was mostly to look at the aqueous and climatic and geologic history of a site in some detail. We selected Gusev Crater, which is a filled crater at the mouth of a 1,000-kilometer-long channel called Maudim Vallis that looks like it drained a big chunk of the highlands, entered in and filled this crater with what we expected would be layers of sedimentary rock. And those sedimentary rocks would then carry the record of the aqueous history of this site. That was our hope. That was not achieved. And here's Gusev, where we started getting high-resolution images in some detail. Here's the mouth of the channel and a potential delta, and our ellipse at landing, and maybe 100 kilometers or so across. The second site was Meridiani Planum. It is the one place throughout the entire Mars that has a TESS, or a thermal infrared signature, that indicates the presence of a gray hematite that typically, but not always on the Earth, is deposited in water. And so here is this beacon, if you will, on the whole planet signaling, come here, water is present, land here. So we did. Here's our ellipse with the data that we got. And we made broad predictions on these landing sites using that remote sensing data. Again, safe for landing, safe for roving. You don't want to go there any other way. Meridiani, we said, would be completely unlike any other landing site with very few rocks and no dust, a dark plain of sand and granules with, again, very little rocks and very little dust. And Gusev would be broadly similar to the Viking landing site. So this is the first image from Meridiani. It's looking down the mast cam, and in the back you see this gray dark plane composed of sand and granules, and I was the happiest guy there was, because that was prediction 1. And here's prediction 2, sort of generally similar to the Viking landing sites with fewer rocks and a little bit dusty. Phoenix was a whole different kettle of fish. We said, okay, sort of similar, again, aeroshell, parachute, radar, but now you have legs. And the height of these legs above the base pedal is how high a rock you can handle. And the answer is that you can handle a 35 centimeters to 45 centimeter high rock, which is maybe twice as wide as that if it's a hemisphere. And these then big solar panels go out and sweep out 2-meter areas on either side that now can't have rocks higher than a half a meter because that would impede the opening of your solar panels. So that basically gave us all about rocks. We had to have as low rock abundance as possible. The trouble is the areas that we were considering are all in the northern hemisphere to get at ice just below the surface, which was there, in fact. But we had no estimates of rock abundance in the high northern latitudes. So we had to sort of say, well, gee, we don't see anything here that looks like it's rocky, and maybe it's going to be okay. And that was fine for the first 2 years of landing site selection until the first high-rise image came down from Mars Reconnaissance Orbiter, which started imaging things at 25 centimeters per pixel. And the whole world changed. Here's one of those first images, and there's a rock that we sent to Mars. That's Viking Lander 2. Well, I know how high that rock is because we built it here in America. And the shadow length there is exactly, if you measure that shadow length, you know the angle of the sun, you can figure out how high it is on Mars. Okay? So we did that. But also look at all these other shadows. So if this is a big shadow rock, what about all these other things? And it turns out everywhere in the northern plains had images just like this. Rocks everywhere. And what became, what we'd hope, a very straightforward site selection, became an hysterical race for a place that didn't have rocks. How do I know those are rocks? Well, here's the image from VL2. Here are the biggest rocks in the scene that we saw. Here's their diameters. Here's the map with those biggest rocks. And here's that map down on the high-rise image. So there's VL2, and there's those rocks, and every one corresponds to one of those shadows. So, okay, if we can see these shadows, we can now measure the size of the rocks. And we did that. So basically, we said, how can we relate the rock abundance we see at the ground, as seen in these images, to what we see in the high-rise image here? Well, let's measure them both ways and see what we find. And we had a model, which is the cumulative fractional area versus diameter of rocks, that would tell you the size or the percent area covered by rocks bigger than 1 meter in diameter. So here's VL1 site, and here's VL2 site. We built a model that had 5%, 10%, 20%, 30%, 40% rock abundance, and had this exponential drop-off, so that at 1 meter diameter, for an area like Pathfinder, which is in black, or VL2, we would expect about 1% of the area was covered by rocks greater than 1 meter in diameter. So now you have a quantitative way to estimate. And most of the ways, we did it from thermal differencing techniques, we actually matched pretty well. But now we can see those rocks directly. And so what we did is we counted the ones from the lander, and that's shown in black. And then we counted them 4 different ways from the orbiter images, and they fall directly on these basic lines, between 20 and 30% rock abundance. So now, this roll-off here is a typical resolution roll-off at about 1.5 meters. You typically need about 5 pixels to identify an object on the surface. So 25 centimeter pixels, you need about 5 of those. You can probably image down to about 1.5 meters diameter. So if you measure this part, you can extrapolate up along these curves to what you would expect at the surface. So you couldn't measure all those by hand. You didn't have enough graduate students. So you had to figure out a better way. Fortunately, Andre Suertes in the machine vision group at JPL figured out a way to segment the shadows. So here's a rock with a shadow. Segment the shadows, fit an ellipse to the shadow, a circle to the terminator of the rock, and from that generally get the diameter and the height in an automated fashion of every rock found. We did this, we measured the rocks, the landers and rovers, and we got the same answer to about plus or minus a pixel, which is as good as you could do, and we wound up measuring more than 10 million rocks in the northern plains looking for a landing site. So here's a high-rise image. The tone is these darker shadows for the rocks. Here are 3 samples from that, and here is a supervised classification of low rock abundance, lighter tone, versus higher rock abundance, darker tone. And here are the counts then from the samples, and from every image, from every rock in that image, all 65,000, you can see they follow and track these model distributions quite well, and they all roll over at about 1.5 meters. So you can measure the rocks here and extrapolate back. How well did we do? Here's the landing site for Phoenix. We predicted because it was green there'd be no big rocks. There's no big rocks. We measured the distribution from orbit and at the surface, and they all fall along these same model curves. So that tells us a way to estimate the rock abundance at the surface directly from the high-rise image. And from that then became a general effort to relate the ground truth that we see at the landing sites to what we see in the remote sensing data. Can you relate them? Can you use those as a predictive tool? And the answer is yes. Okay, here's the paper. And basically, I claim there is a direct relationship between the physical properties of the surface materials at the landing sites and what you'd expect from orbit, the thermal inertia, the albedo, the soil type I just talked about, the rock abundance, the slope, all agree, and it allows you to go back and forth. So let's get into it. Here's the thermal inertia of Mars, basically most of the lower latitudes. You see that there are extreme areas of extreme low thermal inertia. Thermal inertia is the resistance to a change in temperature. So low thermal inertia materials change temperature very quickly. They have very small size and or not much thermal mass. And this suggests that these areas are composed of significant quantities of dust. Atmospheric dust, micron in size or smaller, that's just kind of sitting fluffy on the surface. We've come across these at 2 of our landing sites. It's not load-bearing. If you tried to step on it, you would sink right through it. Viking Lander 2 footpad disappeared below the surface in this dust. It was never seen. They took an image. The second image they took was of the footpad, and they couldn't find it. And it was down beneath this dust. So you don't want to land on this unless you don't mind sinking out of sight. We took the thermal inertia, we now being the global community, and defined different units, and we'll call them A, B, and C. A is dusty, B and C I'll define here in the total albedo versus thermal inertia of Mars. So this is all of Mars now in a simple plot of albedo versus thermal inertia. Lower thermal inertia this way indicates finer grained particles. A higher albedo this way indicates brighter particles, which are also that dust. So unit A here, so A, B, and C constitute 80% of Mars. A is dust. And the estimates of how thick that dust is anywhere from 1 meter to actually tens of meters thick. So sending any kind of lander that you wanted to communicate with after landing into a dust pit was probably not a good idea. So we say we don't want to land anywhere on Mars that's unit A for obvious reasons. And here are the landing sites that we've landed at. The other 7 are all in B and C. So let's talk about B first. It has lower albedo and moderate thermal inertia. So you would predict it's very undusty, if you will. And in fact, Opportunity, which I'll show you a picture of very shortly, landed in one of the lowest dust regions on the planet. It's as dark as it gets, and there's virtually no dust at that place. Whereas these intermediate areas, C, have moderate thermal inertia and intermediate albedo, so they have thin films of dust but not meters thick. And that's where most of our landings have occurred, are in that unit. MPF, Pathfinder, and MSL are similar to C, but with higher inertia. So here's thermal inertia. It's defined as the square root of the thermal conductivity, the density, and the specific heat. And this is the most important, because how heat is transported is by how much those particles are touching together. If you cement it together and create a coherent rock, it's going to transmit that heat very much better than they will otherwise. And that relates directly to the physical properties of the material. And you have your choice of increasing the particle size or increasing the cohesion, how much you cement those things together. So here's a graph of thermal inertia in different units, but you get the idea, versus cohesion here or particle diameter here. And for, let's say, a thermal inertia of this, you have your choice of either cemented-like particles like this or sand-sized grains like this. And with no other information, you can't decide between those two. You don't know which is which. But you know that if you have an inertia down here, a bulk inertia, you don't have too many blocks of rocks because they're going to skew your total inertia. So to first order, your thermal inertia tells you about either particle size, if it's unconsolidated or cohesionless, or it tells you how cemented the material is. Rock abundance, you can also estimate from thermal differencing. The total rock abundance is estimated from these data sets is generally low, less than 20%. So this doesn't have a big lever arm on the total thermal inertia. It's mostly the thermal inertia of the background particles. And if you know the bulk inertia and the rock abundance, you can then define the thermal inertia of the fine component, that is the soil amount directly. And we've done this for all the landing sites, and we basically match the rock abundance, the fine component thermal inertia as expected, as well as the bulk inertia. So here's what we find. We find a variety of different kinds of materials. These are just like any garden variety low cohesion soils on Earth. They have very low cohesions and pretty moderate angles of internal friction. They have a little bit of cohesion. This is a wheel well dug by the Opportunity rover. Here's a Spirit rover section of a bed form that shows a poorly consolidated material, a little bit of crustiness up on top, a little bit of crusty particles at VL2, and some weak cohesion materials there. Stronger materials also have been found. These are stronger soil-like materials at VL1. This is a very strong material, Scooby-Doo, at the Pathfinder site that shows up as this bench of cemented material. And the strong high inertia of MSL is almost certainly due to these conglomerates, which were just below the surface that were found right after landing. The albedo trends exactly with the amount of dust cover from lowest albedo opportunity to higher dustinesses. You can see between being a dust devil track and not a dust devil track at Spirit. VL1, here's the compendium we have all the way up to fairly dusty locations. Again, thin films of dust, but not significant dust cover. And that all relates directly. And so you can actually define the physical properties of the materials that we have investigated on Mars, and they're not that different from the physical properties of materials that we investigate here on Earth. There's drift material, there's sand that are in bed forms, there's these two classes of soils, there's volcanic rocks and sulfate rocks, and you can write down both densities and grain sizes and cohesions and angles of internal friction and albedo, and even what the thermal inertia. And you can add them all up for the landing sites, and you get a pretty good match. We also looked at slopes at both 1 kilometer and 100 meters. The 1 kilometer is my favorite slope test. This was done for the Mars Pathfinder lander, where the engineers took a fully inflated airbag-clad lander into the east parking lot of JPL, and they put it on the edge of a truck, and they pushed it out of the truck down the ramp. And it rolled, and it rolled, and it rolled, and it rolled, and from the data that they got, they predicted that if that Pathfinder lander were to ever land on a smooth asphalt-covered surface on Mars with a 1-degree slope, it would never stop rolling. So we said, okay, that's a big problem because we know that Mars has lots of smooth asphalt-covered surfaces, right? No. But anyway, we measured it, and we can compare then the 1-kilometer slope and the 100-meter slope of the various surfaces, and basically we can order them from smoothest to roughest according to these measurements and what we found. In addition, we have slopes at 1 to 5 meter length scales from stereogrammetry, stereo images, and again we can order them from smoothest to roughest, and we've looked at the radar data we have as well, and that also allows you to make predictions about the bulk densities of the material, the RMS slope, and how the echoes are coming and whether they are predicted from the rock distributions. So let's go through them. Here's our 7 sites, and here's their remote sensing criteria as determined from orbit, and here's what they look like. So Opportunity, predicted to be the lowest albedo, the darkest unit. There's no red dust on this surface. It is blue, and this is not a true color, but still, this is a low, dark blue. There's very little dust on this surface. Interestingly enough, the dust falling from the atmosphere is the same at this site as at Spirit. So that means there's some process that's picking that dust up off the surface and getting it back into the atmosphere. So it's dust-free. It was predicted to be rock-free. I don't see any rocks. That constitutes a pebble, not a rock. A sand and granule surface that basically matches what you'd expect from the thermal inertia from orbit. A smooth, flat surface. This is the smoothest, flattest place we've ever seen on Mars. We brought along a measuring stick. That's the back shell. It's 450 meters away. It's 1 meter high. And there is nothing between you and it that is more than 1 centimeter in relief. So I call that the smoothest, flattest place on Mars right there. So there it is. It's a match between what we expected and what we found. The Spirit landing site in Gale Crater was predicted to be in this unit C. It was expected to have relatively low rock abundance, so some rocks, but not a lot of big ones. Expected to be pebble rich with a slightly higher thermal inertia. That's from all those little pebbles. Dust-free portion where you had a dust devil track, so that's where we landed here, with the albedo is sort of moderately low, and not too much relief at the various scales, versus the much higher albedo outside of the dust devil track, which was swept clean of dust. Here you can see we've moved the dust from the rover wheels. This has, millimeter micron thicknesses of atmospheric dust sitting on the surface. Go to Mars Pathfinder. We're going to a slightly higher albedo. You can see the dust is covering more of the surfaces, the rocks. We expected it to be rocky. That is 20% rock abundance, as we expected. Relatively high relief from these streamlined islands, and there's ridge trough topography in the background that was formed by the draining of the water from the catastrophic flood. So that all gives it relatively high relief at the various length scales. The Viking Lander 2, perhaps the dustiest spot. You can see the thin carapaces of dust covering just about most of the area. Expected to be rocky from orbit, and it is, of 18% rock abundance. We actually matched the diffuse scattering in the radar signal from the rock distributions, and a relatively low relief at the various scales. You can see what a flat plane that is. Viking Lander 1, expected to be moderately rocky with the rocks and the outcrop added in. Sort of intermediate dustiness with the albedo, and a relatively high relief. You can see a crater rim here, and so on in the background, all matching basically the thermal inertia and various properties. Phoenix in the northern plains, expected to be very few rocks, and there's virtually no rocks, or very small ones. A moderate thermal inertia. This actually had a 2-layer model that matched the ice just a few centimeters below the surface. Moderate dustiness and relatively low relief at the various scales. And the Columbia Hills, which we drove up into with Spirit, expected to be much higher relief, as seen here. And then MSL was expected to be in Unit C. That's what you see. Moderate dustiness, 0.24, that's what you found. Extensive duracrust was expected. I showed you that cemented conglomerate. And relatively rough. You can see that mound is a kilometer high, or kilometers high, at the various length scales. So all those pretty much match. The MSL site selection was the longest site selection we've had. It took 5 years because the mission was delayed from one launch opportunity. Here's where we selected the Gale landing site, located just on the edge of a mound inside Gale Crater that stands 5 kilometers higher side. This is a much smaller landing ellipse than any of the others because it uses aeromaneuvering to shrink the ellipse. So this is 25 kilometers across. The level of investigation was unbelievable for this site. There basically were no surprises, and I just wanted to give you a hint of the kind of investigations that we were able to do using the data that we got from the Mars Reconnaissance Orbiter. In that sense, we could not only certify that the site was safe, but that where we wanted to go, in that this is a go-to site, was also trafficable and that you could get there. So here's the Gale ellipse, 25 kilometers by 20. Each of these is a stereo pair with 1 meter elevation postings from high rise. High rise 25 centimeters per pixel. 4 of those together gives you about a meter. On the background is a 6 meter per pixel CTX stereo pair and an HRSC stereo pair. And from that, we have virtually complete stereo coverage with slopes at 1 meter length scale, which are shown here. So once you have slopes at that level of fidelity, you can say, well, is that surface going to be trafficable? And the first thing we looked at for a rover like MSL, where you're expecting it to drive tens of kilometers, is you can't have it land in a place that it can't get out of. That's called an inescapable hazard. So the rules for driving are very straightforward. If you have mostly soil-covered material where there's not much purchase for the rover wheels, you can only go up to 15-degree slopes. That's from tests and also as suggested by a variety of other things. So you can see the slopes on the rim of this crater. You can see no rock here. This is all just a regolith-covered surface. Exceed 15 degrees continuously. So if you landed safely in the bottom, you got nowhere to go. I say that's mission failure because you didn't land here to crank around this little crater. You wanted to go to the hills. So this is an inescapable hazard. And obviously, you don't want too many of these in your landing ellipse. So we looked everywhere throughout all of the potential ellipses. Here was an interesting one where the slopes on the edge of the crater were not above 15 degrees. But when you looked at it, they had these giant bedforms. Well, bedforms are made up of sand and cohesionless sand and maybe gravel. Let's show you. This is the rover here. It's right there. The bedforms are huge by comparison. Bedforms are 10 times the size. So you're trapped. You land there, you're not getting out. You can't get out. You can't even get over the bedforms. So this is also what I would call an inescapable hazard. And now you can use this to say, okay, will I actually land and get to where I want to go? And the final part of that is, I don't want what's here. That's not why Gale Crater was selected. I want what's here, because there are layers of clay and sulfate-bearing strata on the bottom part of the mound here. This is as close as you could get the ellipse to that. So you're going to land somewhere in here. You got to drive through a bunch of fresh sand dunes, and you got to get up into these layers. And the question is, can you do that? Well, okay, we got our slope maps. Here's an example of a variety of sand-free paths through these fresh sand dunes. A little bit more detail. So here are the dunes. They have angle of repose slopes. Here's an area through the dune intermediate area that's mostly covered with rock or duracrust that has low slopes that you could pass through. So we believe there are lots of ways through these sand dunes to get to where you want to go. And then you want to get to this clay layer and the sulfate layers here, and we can evaluate the pathways that you have that meet the traversability criteria. And here are a variety of pathways that go up into these various layers. You get up to this material, which is not a fan. And you can see the slopes are higher than 30 degrees. So the rover could never get beyond this. So if you ever hear anybody on the news say we're going to climb Mount Sharp, forget about it, you can't do it, not possible. You're only going to get up to here, and then you're going to go someplace else. But with this many paths that appear plausible, it does appear that you can sample the various strata that you need to. So now we've confirmed that we can actually get to the material we want to, we can get up through the material we want to, and we can do it, not shown here, in a time that's reasonable. Also, interestingly, there's the ellipse, there's the strata you want to get, there's that unit. This is extremely low thermal inertia. This is dust. You couldn't get up there anyway, even if you wanted to. So the rover will spend all of its time down here, and if it gets tired, it will just move along this way. Plenty of stuff to do for sure. Okay, the last site selection is the one we're in now, and it's, of course, the most fun because it's the one you're in now. This is the InSight mission. This is a refly of the Phoenix Lander that will put down a seismometer and a heat flow probe. And it includes, it's a JPL mission, and I'm the co-I in charge of site selection. So here is the landing site constraints, and they are so severe that there's only one place to go look on Mars. So you got to go 15 south to 5 north for solar power. Our ellipse size is big, huge, and we need to be really low to get, and then we have all the other interesting stuff. Except for one that's really kind of interesting. We need a broken up regolith that's more than 5 meters thick to allow our mole a chance to get down. The mole wants to go down 5 meters. So now I not only have to look at the surface, I need to look 5 meters below the surface. You do that. It's not radar, it's images, right? Aha, but wait. Okay, so here's 5 north to 15 south. Anything in red is too high. Anything in green or yellow is plausible, and you just got rid of 99.99% of the planet. So you got your choice of this, or this. Well, if you then map the thermal inertia constraints, which are shown here, you wipe out all of this here, so you're left with just this, and this. Well, we've done this before. You can't get an ellipse that's 140 kilometers into Valles Marinera canyons, and it's very rocky. And this area is very rocky, so this is the only area you have to look at. So let's show you what that looks like. There. Here is that low thermal inertia zone. Here is this square. Anything in black is too high. We've now gotten rid of 99.99999% of the planet, and this is your home right there. And the question is, can you find an ellipse that will work? And there are 16 based on the rock abundance thermal differencing techniques that are below 10% for a safe landing. And here are prospective ellipses that we started to look at. And then we said, well, how do we know we can get down below what is the material made of? Well, we looked at the thermal inertia, and it's all around 200 and fairly monotonous. And for that, there we are in our albedo and thermal inertia space. And there we are in our thermal inertia. We are composed of cohesionless sand, at least through the thermal aspect of a few meters at least, or very low cohesion soils, either of which is suitable for our mole. So the materials are right. Everything looks good. Is it smooth enough? Is it flat enough? Here's the numbers that you can write down from that. We started taking high-resolution images, and we noticed that we had these bright halo craters here. And then we imaged those in a little bit more detail here. And those bright halo craters are aeolian bedform filled and bright because of the sand. Okay. And they have lots of rocks around them, which are not good. But notice that this crater is 200 meters in diameter, and it is excavating into its ejecta from about 10% the diameter. So at 20 meters depth below the surface is a hard rock that is strong enough to get itself blasted out of the crater and deposited on the surface. If that was cohesionless sand, there'd be no blocks there. So there's a strong rock at 20 meters depth. But when I look at small fresh craters, there's no rocks around them at all. So what's happening here is we have a regolith that's probably 5 or 10 meters thick that if the crater is small, it can't get to that strong rock. It's just getting to that regolith. But if it is getting to those rocks, it's seizing that. So we now have a way to measure the regolith thickness at prospective places that we want to land. So see, I've just looked 10 meters below the surface. That's pretty good, huh? So that's our job, is to find smooth, flat, boring place with enough regolith to get our mold down. And here is a 1 in a million high-rise images. Here's our strong layer. You can see it's well jointed. Here is that regolith broken up. There's not many rocks in it, not much different from the number of rocks you see on the surface. That's 10 meters thick. It's sitting on top, and this would be an impact-generated regolith. The surface age is 3.6 billion years. It's just been lots of churning up. So that's what we want, is that broken up regolith. And it's smooth and flat without many boulders except for the rocky ejecta craters. So that's it. Surface is ground truth. I think we can relate the remote sensing data that we have from the planet. From MRO, we have a spectacular tool to get down to the scale that we're actually going to see with the lander. And I think provided that MRO stays functional for as long as we need, with the high-rise and CTX images, we should be able to do a very good job on our next site selection. Thank you very much.